After we analyzed the phenomenon of reflection, we looked at objects that utilize this phenomenon to create images, specifically mirrors, both plane mirrors and spherical mirrors, concave and convex. Well, now that we've discussed refraction, or these bending of light rays as they move from one medium to another, we're now going to look at objects that utilize this phenomenon to also generate images. And these objects are known as lenses. And we're going to specifically be looking at thin lenses today. So I want to start off by imagining we have like a triangular prism here, think kind of Pink Floyd, and let's say we have a laser beam coming into the edge of this triangular prism shape. And we'll say it's made of glass or something, and we'll say this is air on the outside. So the index of refraction of the glass is higher than that for air, so when it strikes this normal line here, well, it's going to bend toward the normal. The light ray is. It's going to bend toward the normal and continue across to the other side, where we'll see, though, we have a new normal because these edges are not parallel. And when we have this new normal, now the light ray is going from glass with a higher index to air with a lower index, so it's going to bend away from the normal, and that's in fact going to cause it to go downward even more. So when we look at this, we see we have a triangular shape, and when it comes in parallel, we'll say to like the bottom edge here, it's going to cause the light ray to bend towards the wider part of the triangle and away from the narrower part of the triangle. So taking that a step further, let's say we've got two triangular prisms here. They're very skinny, but they're on top of each other. And if we have a ray come through on the top, well, we already talked about it's going to bend towards the wider part, so it's going to bend downwards. And if we have a ray go through the bottom triangle, well, it's going to bend upward. And the thing is, though, is that we've, in essence, just created a lens. So a lens is going to look very similar to this, except we're going to basically make it one piece of glass, and we're going to smooth down the edges. So we've kind of got these curves on either side. So a lens is a piece of transparent material. So it doesn't have to be glass. It could be plastic, acrylic, anything like that, that forms images through refraction rather than through reflection. So what exactly do we mean by the fact that it is a thin lens? What we're saying by that is that the radius of curvature of the curves on the edge of this lens is way bigger than the width of the lens, and so that's going to make them a little bit easier to analyze here. Alright, so the thing is, with this particular shape here, we see that I've got on both sides, these are actually convex edges because they don't cave in. They're the opposite of concave, so they're going to be bowed outward. And this is in fact a convex lens. And a convex lens, as we just saw with those two rays, but now we can do it with a bunch of different rays. Incident rays that are parallel to this principal axis that goes through the center of the lens. When they hit the lens, they are all refracted through what we call the far focus. Now, a couple things here that are different from mirrors. One, we have two foci here. We've got the near focus and the far focus. They are the same distance away, but right now we're focusing specifically on the far because all these rays go through that point. And this is specifically a converging lens because we see that all the light rays are coming in parallel to each other. They all converge on this particular point, meaning that it's very, very similar to a concave mirror, because remember, a concave mirror was a converging mirror. So kind of a flip here. The concave mirror and the convex lens are both converging apparati. Additionally, one other point I want to briefly say is that you see this dotted line I put through the center of the lens. That's often called like the plane of the lens or something along those lines. We don't want to bend our light rays until they hit that line. This is a bit of a simplification, but it will make analyzing the lenses much easier down the line. Now, thankfully for us, lenses use the same magnification equation as mirrors. So we have m is equal to hi over h naught equal to minus si over s naught, where everything is the same. Image height, image distance, object distance. And remember that these units just need to be consistent. And the same trends hold as well. If it has a positive image distance, it is real. A negative image distance, it is virtual. And if you have a positive image distance, you are left with a negative image height, so it is inverted, so those go together always. And if you have a negative image distance, you'll have a positive image height, meaning it will be upright, and virtual and upright are also always going to go together. Additionally, we also can continue to use the mirror equation. However, I should go ahead and tell you that this usually is not called the mirror equation. It's in fact usually called the thin lens equation. It just happens to also work for mirrors. So 1 over S naught plus 1 over SI equals 1 over F. The exact same thing here, exact same equation. Now the one big key difference here, and this is something we got to get used to, is that the object distance will always be positive. However, when we look at images from mirrors and from lenses, for mirrors, it was a real image if it was in front of the mirror, basically near the object. For a lens, it is a real object if it is on the opposite side of the lens from the object, because the light rays are going through the lens, they're not reflecting off of it. So we're going to say that the image distance is positive when the image is on the opposite side of the lens from the object. So the light rays have literally gone through and they've converged. It is a negative image distance when that image is on the same side of the lens as the object is. And we'll see this a little bit more in a second. So let's look at an example. Let's say we have a 4 centimeter tall object represented with this arrow, so h naught is 4 centimeters, that is placed 12 centimeters, so s naught is 12 centimeters, from a convex lens, so the sides are bowed out, with a focal length of 6 centimeters. So that means that this distance here is 6 centimeters, this distance here is also 6 centimeters. And we want to know, okay, what is the image distance and the image height of the image created by the scenario, and is this image upright or inverted? And additionally, is it real or virtual? So let's start off by looking at the thin lens equation, and I'm going to rearrange it to solve for this image distance. I'm going to move 1 over SO across, and I'm going to take the 1 over power for the whole thing. And when we do this, let's go ahead and plug our numbers in. We already have them all here. So 1 over 6 centimeters minus 1 over 12 centimeters. And then we're going to take the whole thing to the minus 1. And we get an image distance of 12 centimeters. So notice this is a positive 12. So it's going to appear on the opposite side of the lens from the object. So the image is going to appear over here on the right. Now, to figure out the image height, we use the magnification equation. We solve for image height, so we're going to multiply that object height across and just stick in numbers again. And we're going to get minus times 12 centimeters times 4 centimeters over 12 centimeters. Well, these are going to cancel. And so we will get an image height of negative 4 centimeters. So it's going to be downward this way. In fact, it will be inverted because it is a negative sign. And additionally, if we want to know if it's real or virtual, well, this is a positive image distance, so it is a real image because the light rays coming from this object, they're going to go through the lens and physically converge at this point here opposite the side of the object. So because this light is refracting, it will still converge even though it's on the opposite side of the lens. So let's go ahead and do the same thing again, but now we're going to move the original object, it's the same height, to a distance that is 3 centimeters from the lens. So the object distance is now 3 centimeters rather than 12. And we're going to do the exact same thing. So I want you to go and pause the video, give it a shot. Let's see what you come up with. Well, hopefully you tried it out, and let's see what we do here. So, okay, to figure out the image distance, we are going to use, once again, the thin lens equation, and we're going to solve for it the exact same way. So we're going to get 1 over 6 centimeters minus 1 over 3 centimeters to the minus 1, plug it in our calculator, and you will see that comes out to be minus 6 centimeters. So what this is telling me is that the image is going to be on the same side of the lens as the object, specifically 6 centimeters away. And now to solve for the image height, we go ahead and use our magnification equation. We stick everything in. Now, one thing to keep in mind here is that this has changed and this has changed, both in this equation. So we have minus times negative 6 for the image distance times 4 for the object height over 3 for the object distance. And we get a image height of 8 centimeters. And this is positive, so that tells us it is an upright image. And we should go ahead and know, okay, if it's upright, that means it must be a virtual image. And this is in fact the case because it is a negative image distance. So it is actually going to not really be composed of light rays converging here. So the light rays are going to diverge on this side of the lens. So we have to backtrack. We have to take these refracted rays and back up until we reach this virtual point here. And this is where this image would in fact form. So let's go ahead and notice a couple of trends we've already seen with these convex lenses because they're going to be pretty universal. Now you don't have to memorize these, but it's good to at least keep them in mind. So when we are within the focal length of this convex lens, when the object is within this focal length, the image will always be virtual, upright, and magnified. Meaning that we will always get a bigger image than the object actually is. And this is actually basically the principle of how a magnifying glass operates. You get real close because you have to be within that focal length, and that will cause the image to appear large. Now, when we are past the focal length of this lens, when the object is located past it, the image will always be real and inverted. Now, the magnification will vary depending on the scenario. Now, there's a couple of different things that utilize this principle. One, I'll go ahead and say, are most objective lenses. So an objective lens is otherwise known as a light gathering lens. So if you have a camera, a microscope, a telescope, anything like that, it brings in a lot of light that is essentially parallel, and it's going to converge it to a single point, whether that is like some sort of light detector or something along those lines, that can then help formulate images. Our eyes actually operate on the same principle. Our eyes actually have a lens in them. Now, that lens is not made of glass or anything like that. It's basically a film that is filled with liquid, and now allows light rays to refract and go to the back of our eyeball on the retina that then allows us to see things. We'll learn more about the eye later, but a big thing I want to note here is that notice this always says the images is real or inverted. So your eye actually detects images, or actually sees images, that are flipped upside down, but our brain essentially knows to flip everything right side up because we are used to being oriented this direction. Now let's return to that earlier scenario looking at these triangular prisms, but now rather than having the two wide edges on top of each other, let's put the 2 points on top of each other so we get something that looks like this. Well, now if we bring an array through the top one, well, remember it's going to bend towards the wide part of the prism, so it's going to bend away, and if we have a light ray go through the bottom one, it will also bend away, and we can see that there's no converging happening here. In fact, these two diverge away from each other. But if we were to backtrack this refracted rays backwards, if we were to take them backwards in a straight line, we would actually see that they converge on this initial side of the lens at a particular point. And that would in fact be the near focus, because what we've just created now is a thin lens that is specifically a concave lens. A concave lens is thinner in the middle and wider at the edges so that each side is bowed in or each side is caved in, so concave. And what we saw is that incident rays parallel to this actually diverge away from the principal axis on the opposite side of the lens, which is why this is a diverging lens. However, they diverge in such a way that they're actually refracting as if they originated from this near focus rather than the far focus. And once again, this is very, very similar to something we've already seen. This is in fact incredibly similar to a convex mirror. So a convex mirror and a concave lens also operate very, very similarly because they are diverging. Now, one other thing we want to note on this is just like convex mirrors, concave lenses we define with a negative focal length because the light rays are basically diverging as if they originate from the near focus. So we're going to say that focal length for this type of lens is in fact negative. And that's very, very crucial. It's very, very easy to make a mistake there. Thankfully, though, we use the exact same magnification and thin lens equations. So go ahead and give it a shot with this new scenario. We have an 8 centimeter tall object that is placed 9 centimeters away from a concave lens, so it's bounded on each side with a focal length of 6 centimeters. So each of these focal lengths is 6 centimeters. We have an 8 centimeter tall object, and it is located 9 centimeters away. We want to know the image distance, image height. Is it upright or inverted, or is it real or virtual? So go ahead and once again pause the video, give it a shot. Let's see how you do. Okay, hopefully you tried it on your own. And remember, the real key difference here, and this is a very, very easy way to make a mistake, is that the focal length of a concave lens is negative. So when we have our f in this equations, we're not going to use 6 centimeters, we're going to use minus 6 centimeters. So let's start off with the thin lens equation. I'm going to rearrange it once again. For SI, the image distance, I'm going to go ahead and solve. 1 over minus 6 centimeters minus 1 over 9 centimeters to the minus 1. If you stick that in your calculator, you get an image distance of negative 3.6 centimeters. So it's going to be on the same side of the lens as the object. Now we go ahead and solve for the image height. Let's go ahead and stick it into this equation. And we're going to get, okay, so the image distance was negative 3.6 times the object height, which was 8, over the object distance, which was 9, positive 9, always positive, multiply the whole thing by -1, and we get an image height of 3.2 centimeters, which is positive, telling us it is an upright image, which makes sense because we would expect this to be a virtual image because it is on the same side of the lens as the object. The light rays are once again not actually converging here, they actually diverge on the opposite side, but if you were to backtrack them, they would appear to converge at this point. And just like how convex mirrors were in a lot of ways simpler than concave mirrors, well, concave lenses are simpler than convex lenses, and they really only have a single trend, which is that all images produced by concave lenses are virtual, upright, and reduced. They're going to appear smaller. So you might be thinking, why would I want that? Well, there's a couple of different reasons. One, we use these in, for instance, peepholes. With peepholes, that allows you, even though they appear smaller, allows us to broaden the amount or the field of view that we can see, so you can see more outside your door. You also see them in some eyepiece lenses, in like binoculars or telescopes. Basically, they just help focus the image a little bit more for you. So essentially, if the image has been converged too much, it helps diverge it back out so you can see it a little better. And we also use them in conjunction with convex lenses to try to correct some image distortions and things like that. But they're definitely far, far less common than convex lenses. So that concludes our lesson on thin lenses, and at this point we want to make sure we can do a few things. Can we describe the properties of convex and concave lenses, aka things like their focal length, and are they bowed in or bowed out on the edges, including how they specifically refract light rays. So remember, convex lenses cause them to converge, concave lenses cause them to diverge. Can we utilize the thin lens and magnification equations to mathematically analyze thin lenses, just like we've done previously, keeping in mind that the focal length of a concave lens is negative? And can we identify properties of images formed by thin lenses, such as 1, are they real or virtual? 2, are they upright or inverted? And 3, are they enlarged, reduced, or to scale, depending on their specific magnification?